especially on micro EDM, micro FSW, and additive friction stir processing. Dr. Saha has also been working on 4 projects funded by several funding agencies. Several peer-reviewed published international journals, book chapters, and conference proceedings to his credit. He has also delivered several invited talks to various prestigious institutes all over the India. So far as the context of this particular FTV is concerned, we are fortunate to have Dr. Saha with us today. I am thankful to Dr. Saha for accepting our invitation within a very short span of time. I hope we are going to have an interesting session now. So on behalf of Department of Production Engineering, VSUT Burla, I would like to request our head of the department, Dr. Pal, to invite Dr. Saha to this session. Please, sir.
Thank you. Welcome you once again, Dr. Saha. And before going to discuss or going to brief outline of Probir Saha, is one of my close friend, and he has done a research work on non-traditional machining during his PhD work, and he has a lot of knowledge in the evolutionary non-traditional multi-objective optimization techniques, and most probably he will discuss different case studies oriented on this particular area. I am very thankful to him that within very short time he has agreed with our request. Thank you, Saha. Dr. Saha, please, you may start your proceedings. Thank you.
Yeah, so first of all, I would like to thank Professor Kamal Pal. As he said, he is one of my closest friends too, because we both did PhD under same supervisor and almost at the same time. We also did our graduation from Production Engineering Department, so we are also classmates. And I would also like Professor Mahapatra also for this invitation too. Although it's very, it was a very limited time which was given to me. As Dr. Mahapatra said, that my current research is on microfabrication, which mainly on micro EDM, micro FSW, and also to some extent additive manufacturing, particularly based on solid waste. Now, the topic which I was given, I was asked to present, that was very interesting topic for me also, because that is the work I did during my PhD, that is non-dominated sorting genetic algorithm, and that process I have used in one of the non-conventional machining processes, which I'll definitely discuss on that. And yeah, so I can start right now. I've already shared my screen. I don't know whether it is visible or not. Can you see it, please? Could anyone tell me whether my screen, my slide is visible to you or not?
Yes, sir. Yes, sir. Yes, sir.
Okay, fine. So, okay, so the topic which I have chosen is, or which I was given, is multi-objective optimization using evolutionary algorithms. So evolutionary algorithms, the name itself, it says that it is something different than conventional optimization algorithm, and it also works differently. So we will restrict ourselves particularly on multi-objective optimization only. Now, if I see most of the optimization problems, either some of them are single objective and some of them are multi-objective. Now, in case of single objective, the objective function is definitely 1. And in case of multi-objective, the objective functions are definitely more than 1. Now, in single objective, generally we obtain one solution, and in multi-objective, we get multi-solutions. So that is a very important aspect. In multi-objective optimization problem, we get multiple solutions. Now, multi-objective optimization does not find an optimal solution corresponding to each objective function. So there can be a kind of misconception that it may solve individual objectives one by one, and they will get solution, one optimal solution for one objective, second optimal solution for second objective, and so on. But this is not the case. All the objective functions are I would say, considered simultaneously. Now, before proceed to detail of this evolutionary multi-objective optimization, as we have used this terminology objective function, what do I mean by objective function? System, if you see, has a typical goal, and the goal is achieved by controlling the process parameters. And this is done by obtaining a functional relationship between the input and the output decision variables. So for example, in this case, if I see this figure explains a simple straight turning operation where you can see here, I can use this one also. Yeah, you can see that one workpiece, cylindrical workpiece, which is rotating, and at the same time, the cutting tool is given a longitudinal fit with providing some depth of penetration. Now, in this process, if I say goal, what is our goal? The goal could be, I want to maximize my material removal rate. This could be a one goal. The goal could be, I want to have a very minimum surface finish, a very minimum surface roughness or very high surface finish. So that could be also one goal. Now, so I have used a maximization of the material removal rate and minimization of the surface roughness. Now, to do that, maximize and minimize, I want to have a functional relationship. So if I see material removal rate, which is definitely a function of some of the process variables. Process variables are turning, and the process variables could be feed, could be depth of cut, and could be cutting speed. So I want to have a relationship between MRR versus this process parameter. Similarly, I also will have a relationship between surface roughness and this process variable. So when we have this relationship, we call a objective function. So in manufacturing, we often obtain these objective functions either by some empirical formula or by using some regression techniques, some statistical approach. We can get a quadratic or some other sort of regression equations, or sometimes we also use artificial intelligence, artificial neural network, machine learning to map the input-output decision variable. So you have plenty scopes to obtain the functional relationship between the input and output process variables, which defines your objective function. Now, when to use a multi-objective optimizations? So that is very important, and every time, even in IIT Patna, I have seen several times that the students have this misconception. The misconception is that if I have more than one objective, we call it as multi-objective optimization problem. But is it the case? So the answer is no, definitely no. If you have a multiple objectives with respect to some decision variables, you cannot say it is a multi-objective optimization unless until you check the conflicting nature of the objective function with each and every decision variables. So I have used one terminology which is conflicting objective functions. What do you mean by conflicting objective function? So for example, this is a very good example. We have a relationship between comfort, which is given in percentage, and the cost of a car. And I know that if I invest or spend more money to purchase a car, I will definitely get so many features. And one of the important features is the comfort. Out of several, one of the features is comfort. That means if I invest more money, I will get a more comfort. If I invest less money, I will get a less comfort. But if I ask you one question, as a client or as a customer, what I may expect? I may expect that I will invest in a very small amount, but I will get a maximum comfort. Right. So you understand these two objectives are very conflicting, cost and comfort. We have a maximization cost, comfort, minimization cost. So these are very conflicting. The real world does not allow you to do that. You have to invest more to get comfort, right? Now, again, you have to be very careful. I mean, the design engineer, even the process engineers in car manufacturing, they must be very much, confident about their optimal design, that if somebody spends 80,000 rupees, I must give this much comfort. I must give this much comfort, and that is the best comfort I can provide. So you can understand that in this line you have plenty solutions. So this is a multi-objective, and you have plenty solutions, and I cannot say which solution is better than which. I cannot say. So it depends on the choice of the customers. The choice of the customer. So if the choice one, okay, I do not have big money, so I'm not bothering about the comfort. Okay, give me this card. Give me this card. He is very much happy. But that is the best. That is the best. It's not like the solution is getting from here or the solution is getting from here. This is the best solution. Similarly, someone is interested, okay, I have huge money. I can spend more money for that, so I need a maximum comfort. I'm interested in the comfort. So he can go for that, but that is the best solution. So that means the solution is not lying here. So in designing of the car, there could be million of solutions against cost and comfort, but they have to do a proper optimization so that whatever the solution they will get, cost versus comfort, that will be the best one out of the million solutions. So that has to be confirmed, and that is where the multi-objective optimization is indeed playing an important role. So going into another one, this will be easy for understand. If you see a mathematical expression with conflicting objectives with respect to mathematical expression. If you see of two functions I have given, so f1x and f2x. So f1x is x1 and f2x is 1 plus x2 by x1. And the boundaries are x1 is varying from 0.1 to 1 and x2 is varying from 0 to 5. Now, interestingly, if you try to minimize x1, automatically, if you are not changing x2, automatically it will maximum f2. But what is your requirement? My requirement is that I want to have minimize f1x and minimize f2x. So that makes these two objectives conflicting with respect to x1 at least. So that is what you have to check when you go for applying multi-objective optimization. So this part has to be checked before you go for multi-objective optimization. Otherwise, you will converge with a single solution. Maybe you have 3 or 4 solutions and they are not conflicting in nature. So with the decision variables, so a single solution can satisfy all the objectives. You need not go for multi-objective optimization. Okay. Now, if you see the turning operation, again I have used. So we have a MRR and we have a surface roughness. Now, if you see the MRR have a different process variable, surface roughness also have different process variable. Now, by tuning this process parameter, if you want to try to increase the MRR, you will see that RA value also goes high. But what is your requirement? As a process engineer, your requirement is also to have a minimized RA. So I can say the objective function MRR and the objective function RA, they are conflicting each other with respect to this process variables or decision variables. So I can treat it as a multi-objective optimization problem, and I can use any of the either conventional, classical, or evolutionary multi-objective optimization techniques. Now, let's see a non-conflicting objectives, just to have an idea of that. I hope I am audible, right?
Yes, sir. It's
Yeah, yeah. And the sound is very clear, right?
Yes, sir.
Yeah, fine. So I can go ahead. Now, if you see a mathematical expression, say a non-conflicting objectives. So we have again two objectives, f1x, f2x, same equations, same boundary. But what I did here, I put maximize. Now you see, if you try to minimize x1, automatically f2 will be increased. So this will be done. So that means you will have only one solution of x1 that will satisfy both this and this objective. So it's a single objective optimization problem. It's not a no more a multi-objective optimization, right? So what I can conclude at the end of these 3-4 slides is that multi-objectives doesn't mean that problem has more than one objective functions. What is important is to check the conflicting nature of the objective function with the decision variables, and that is foremost important before applying any multi-objective optimization tools. Now, let's see, there are also several classical multi-objective optimization techniques. They are, say, weighted sum, epsilon constraint, weighted metric, Benson's, value functions, goal programming, interactive. So, I mean, these are the techniques which have been developed by the researchers, has been reported in the original article. And if you see a book written by Professor Kalyan Mahadev, he is the pioneer in this genetic algorithm in India. So for India is concerned, and even I would say the worldwide is becoming very a renowned person. He has become a renowned person so far as his genetic algorithm is concerned. He was also the PhD student of Goldberg, who is the developer of genetic algorithm. So he has written, Professor Kalyan Mahadev has written 2 books. If you see, one book is on multi-objective optimization. And if you go through that, you will have a detailed analysis or detailed explanation of each and every techniques. So I shall not go into that because this is out of scope of my presentation. Now, if you see, just I can generalize that if you see all these techniques, either they work on direct search or they work on gradient based search. Now, so there are limitations of these techniques, and indeed they're truly limited. I mean, they are truly possess some limitation. The first one is that all this the classical algorithm means, what do you mean by classical? It means after each iteration, the solution of the previous solution gets updated. So when in optimization techniques, this approach is used, we call it as classical optimization approach. So we can understand that it is actually point by point algorithms and uses a very deterministic transition rule. So the rules to move from one point to another point into the search space, that follows a very deterministic transition rules and proposed by several researchers, right? So that is one point. Second point is that the convergence, it depends on the chosen initial solution. So more the initial solution is deviated from the optimal one, so the convergence rate will be less. Even there could be a possibility that they may not converge, or they converge after a lot of time, so competition and complexity might increase, right? Then the third one, which is also important, that some of the optimization tools is actually developed by solving some typical problems. So when the problem statement changes, that technique may not work. So that means the techniques are not very general, they're not very robust. So that is another problem. Say one example I can give you is possibly goal programming method, which was used for some sort of polynomial equations. When some sort of polynomial equations are being solved, optimized, then goal programming method was very much efficient. But if you move into another one, this may not work. Then the next one is also important, is that not efficient for discrete search space. So even if you do not have the objective function, which is continuous in nature, then this method will not work. And in real world, you see that the solutions may be discrete. They may not follow an equation, but they're very discrete one. And for those kind of problems, you cannot solve because you need equations where the equations must be continuous in nature. Because sometimes you need to either go for derivation. Say for direct search, we generally use the objective function and their constraint function directly into the search space. And in case of gradient descent waves, we do first order, second order differentiation. The derivatives we do, and to get the derivatives, you need to have a continuous function. If the problem statement do not follow a continuous function, then possibly you cannot apply this derivative approach. So that way, it is not efficient for discrete search space. And also, it cannot be efficiently used on parallel machine. Like, we have a CFD, we have NC software there, it works on so many optimization techniques. And there people are exploring the parallel computing, right? One solution taken from one system to another system. But in those cases, as these classical techniques are working on, point by point, so the parallel processing that cannot be explored with the help of this classical optimization techniques. So these are important. These are really important limitation of this process. Now you might be thinking, then how GA can solve these problems? Can GA really solve these problems? So first one is that it works with a discrete search space, even though function is continuous. So it works with discrete search space, which is not the case in case of classical approach, because it works with multiple solution. The initial multiple solutions, and they follow some sort of probabilistic approach, not very deterministic approach, and they can go for anywhere, like anywhere in the solution space, and they are discrete in nature. Now, this is also an EVA content, like string structures, which sometimes we call schema. So one schema means one pattern of chromosome or genotype presentation, which is very common in case of genetic algorithm. In case of particularly binary coded genetic algorithm, so schema is moved. So that means some sort of similarities is moved from one point to another point. Then GA works with a population of solution instead of a single solution, right? That is a very important point. So it's not working with single solution, it's working with multiple solution. Of course, it will all align in the feasible solution domain, and finally it converts to one single solution. The probability of getting optimal solution is also high, and also uses probabilistic transition rule to guide their search. This feature allows GAs to recover from early mistake, therefore can be used to avoid. So in single objective GA, I don't know whether the elitism preserving operator is not that much. I mean, they use a reproduction. They use reproduction to have multiple copies of elite solution. But in multi-objective GSA, NSJ2 will explain later on that it intentionally contains one elite preserving operator, which ensures that the good solution will never die. They will carry forward in the next generation. So elitism is essentially maintained in case of multi-objective genetic algorithm. Now, this is just typical, just to give one glimpse of what do you mean by weighted sum method, is that we have a two objective function, which is minimize x1 and maximize, no, this should be not maximize, this should be again minimized, because the objective functions are to be minimized only. GA also works for only maximization problem. Sometimes we convert into one by that part so that we can convert the minimization problem to maximization. Anyway, but it should be minimized because this objective should be conflicting in nature. And then what we do, we actually combine these two objective functions, you can see, and introducing some weight vectors. So weight vectors varies from 0 to 1. So you can solve this problem. Say for you given a 0 and it is 1. So and solve this problem, you will get some solution. Again, you suppose you given 0, 0.5, this is 0.5, or maybe 0.4, this is 0.6, something like that. So you can understand that when the demands changes, like when the demand changes, one example is definitely, say in machining, sometimes we are very much interested on rough cut, sometimes we are very much interested on finishing cut. If we go for rough cut, then the MRR is most important. When you go for fast cut, finishing cut, then the surface finish is important. So accordingly, you can set your the weight vector. Suppose the first one is suppose MRR, and this is surface finish. So you can understand when you go for rough cut, I will give more attention here. So I will increase the weight vectors and maybe 0.8 and 0.2, right? So I'm not very much interested in it. So you get a solution. So something like that, weighted sum method works on that. Now next is why multi-objective GA. So first one, you can understand the single weighting method or the weighting method I have explained is sensitive to the weight vectors and needs prior knowledge to the problem. So this is very much important. You need a prior knowledge to the problem, and also you need a weight vectors. That's I've just explained in the previous slide. In real situation, user may require different alternative solutions, right? So they are not interested on one solution. They are interested on various solutions, and the solution should be made available. It's not like, I need this one, so I'll solve this problem, and again, I'll get another solution. So they do not have that much time in design engineer. You must have this optimal solution, the best solution, multiple solutions should be available. So I will choose, as per my requirement, I choose, one after another one, right? So this is why, multi-objective GA, because multi-objective GA will ultimately give you a Pareto solution. So we'll discuss on that, what is Pareto solution, which is the best among, if you have a 1 million solution exist, so that maybe out of 1 million, you will get 100 solutions, suppose. And that 100 solution is the best among 1 million solution. So that's what, multi-objective GA will do for you. And mind it, you cannot say which solution is better than other. In Pareto front, every solutions are equally important, and you cannot claim like you cannot claim that say solution X is better than solution Y. No, all solutions equally important. So it depends on the choice of the customer. If the customer want that solution corresponding to some requirement, you will just pick up one solution out of the 100 Pareto solution, right? So this multiple objective GA does this work for you, and that is very much important, because you will never lie into the local optima. You are interested on the global optima. So that is guaranteed with the help of this multi-objective GA. Now, same problems need to be solved for a number of times, which is time consuming. We have explained this. These methods fail when the objective function becomes, become discontinuous. That means in the classical approach, we have seen that all. And then GA is able to capture a number of solutions simultaneously, because it works within a population, right? It's not a one population, it works with a many population. It depends on you. You can go with 100, you can go with 200, you can go with 1,000. But if you increase the population number, the complexity or computational time will increase. That's it. Now, even in evolutionary multi-objective GA, we have several techniques, right? Even those things, you can get it in the book written by Professor Kallarmadev. Now, some of the multi-objective GA are non-elitist, and some of the multi-objective GA are elitist, right? So this is the evolution through the research, is going on even till 2000. I would say 2000 till 2000 or 2001. People are mostly interested on non-elitist. Now, slowly, people have started moving elitist, and that's become, a very regular aspects of multi-objective GA. Now, what do you mean by non-elitist and elitist? Now, non-elitist means, as I say, that you must ensure that first of all, I would just like to say, because I can assume that the audience who are there, maybe somehow they have a knowledge of at least single objective genetic algorithm, right? Because this is important, because I may not go into details of single objective GA. I shall strictly move into multi-objective GA, but again, I can brief little bit. Now, in GA, it's actually the working principle is similar to our, natural genetic system, right? You have parents, you have children. Parents, the reproduction happens, and then children occurs, and from the children they become again parents, and they can again given children. The children are the solutions, right? And you have also natural mutation, crossover, gene-wise mutation, crossover. Those things also happen, and that promotes to have a better solution. But some of the objective optimization, you can see that it may happen because of mutation, exchange of some bits at some position, or crossover of some bits at some position. The good solution is lost. In the next generation, the good children lost and the bad children has come. If it is going into that track, then possibly you will never achieve the global optimal solutions. And you may start to a local optima, and that will not fulfill your purpose. Now, under this category, we have a Vega, vector evaluated genetic algorithm, multi-objective genetic algorithm, niche Pareto genetic algorithm, and non-dominated sorting genetic algorithm 1. So this is also developed by Kollan Mahadev and his students in NSGA1, but now it is stopped because it is non-elitist. So nobody is using NSGA1. But if you go into NSG elitist, here some sort of elitism preserving operator that is included in their algorithm, which actually ensures that a good solution never will be lost. They will definitely go to the next generation guaranteed. So when it is guaranteed, then we call it as elitist multi-objective GA. And one of them is NSGA2, non-dominated sorting generative algorithm 2. Although I must mention one point here, there is a huge difference between NSGA1 and NSGA2. You might be thinking, if you know NSGA1, you will understand NSGA2. No, there's a huge difference. But still, they kept their name NSGA2. The reason was, just to show the world that the NSGA1 has motivated them to develop NSGA2. So NSGA2 is also developed by Professor Kallan Mahadev and his students in the kernel lab of IIT Kanpur. Then there's a distance Pareto genetic algorithm, multi-objective Messi genetic algorithm, multi-objective microgenetic algorithm, and so on and so forth. And today we'll see every day new genetic algorithm or new algorithm comes. It's very difficult to handle this because everybody is developing new algorithm and claiming that their algorithm is better than the others. Now, this is what I'm trying to explain, that in elitist MOGA, particularly NSGA2, recombination, this is actually added. This is one added feature. What is recombination? Offspring and parent populations are kept combined. So offspring, and so it is not like that, from the parent, after reproduction, crossover, mutation, whatever the children's solution you got, it may happen that the good parent is lost. No, to do that, the offspring and parent both are combined, and then out of this you choose the best, whatever the solution initially you have started with. So maybe you started with 100, and after reproduction, we call it selection, crossover and mutation, maybe you have got another 100. So 100 plus 100, 200 you combine, and then out of this 200, again you pick the 100 solution out of 200. So that guarantee you that, although it's very simple, it's not very difficult, and to understand is very simple, but algorithm-wise you have to implement. And so therefore, even in the next generation, maybe some children are bad, and some parents would have been good. So the good parents will there, and the bad children will go there, because you are again selecting 100 out of 200. So that is important in case of elitist MOGA. Now, as I did work on NSGA2, so I shall focus my next few slides on understanding of this non-dominated sorting generating algorithm too. But before that, let's show one what is called again. It's not working. Okay. It's not working. Okay, so I may skip this for the time being, and maybe we can show from here. Oops. Yeah, I hope my PDF slide is visible to you.
Yes, sir.
Yeah. So we'll start from here. We'll start from here. So we have a random binary initial population. So I worked on real coded. It could be real coded. It could be binary coded and real coded. I worked on binary coded. So binary coded means the initial populations are in the form of bits 0, 1, 0, 1 combination, right? So random binary initial population P of size n. That's I have to choose. So generation start, decode the population because you have started with binary code. So the binary code has to be converted into the real value with the help of some sort of linear interpolation. I will explain that one. Then this is the flowchart actually I have shown to his speaking. Sorry for that. This is actually I have used for neurogenetic algorithm, right? So neurogenetic means I just I have connected neural network and genetic algorithm, multi-objective genetic algorithm combined, and that's what I did. And where I have used this neural network, I have used neural network to find out the fitness function, the input-output relationship, the hidden input-output relationship. That's I have obtained with the help of this neural network, right? And then when you combine neural network with the GA, then it's become neurogenetic technique. So what you have to do is that you have to check whether your population is first classified or not. What do you mean by classification? We'll discuss at length. Classification means you have started with 100 solutions. Now you classify into different rank. Say some solutions are rank 1, some solutions given rank 2, rank 3, rank 4, and so on. Rank 1 solution is definitely better than rank 2. Rank 2 solution is definitely better than rank 3. But any solution lying on a particular rank, you cannot say which one is better than others. So maybe out of 100, you may get 7 such rank, and you understand the rank 1 solution you have the non-dominated individuals. That means that is the solution which dominates. Suppose in the rank 1 you have a 10 solution out of 100, you have a 10 solution which is lying on the first front or front number 1 or rank number 1. So 10 solutions dominate the rest of the 90 solutions. But the 10 solutions, you cannot say which solution is the best among the 10 solutions. So that is the meaning of the ranking. Then after that, when the ranking is done, then we calculate crowding distance. So crowding distance is something like that, which maintain diversity in the solution. So which is very important. In multi-objective GA, what we want, the solution should be as close as Pareto optimal front and as diverse as possible. I mean, the solution should not be concentrated at a particular point, at particular location. They should be diverse. I should not choose a solution, 10 solutions from one single point. I should check only one. I will take other solution from other positions. So that is called diversity of the solution, but relying on a particular front. And this diversity is maintained by using this crowding distance. So I have to calculate crowding distance. We'll discuss on how to calculate crowding distance. And then sorting based on crowded comparison operator. Then we go for, we have to go for a tournament selection, that is the reproduction. So in the reproduction, in case of single objective GA, we use a tournament selection. We use a proportionate selection, say for roulette selection, we sometimes use a ranking selection, but here we are using crowded tournament selection, which is very new, in case of NSGA2. Then we also do crossover and mutation, so it is as like single objective GA. It is as like as, there is no difference. Then we combine them. So that principle, that is the operation which ensures your elitism that is confirmed. So we combine population P plus Q, and from there P plus Q, again I have to choose a P. And when I do P, I'll again do rank them. We'll find out the crowding distance. So we'll apply a crowding comparison operator to pick out of 200 which 100 I should choose. Which 100 I should choose. If all the solution, if out of 200 solution, 100 solutions after some generation, if you see out of 200 solution, 100 solution already have come in the front one. That means you have got the front, we have got the Pareto front. Because 100 solution you want. But it may happen the solution maybe in the first front you have a 15, second front maybe you have a 80, third front maybe you have a 15, something like that. So from first front each and every solution you have to choose, and then from second front you add it up, third front you add it up, unless until the P plus Q is converted into P only. But there might be possibility that for a particular rank, suppose there are solutions where you need only say 10 solutions, but there are 15 solutions there. So I have to discard this 5 solution because I want P solution only. To do that, we will use this crowding operator, crowded comparison operator. So we'll discuss at length when we discuss about NSGA2 more. So now we'll see if generation is completed. Like we have said, generations are 250, 230, something like that. If generation completed, and finally we will come out with only rank 1 solutions, which are nothing but the Pareto optimal solution. So I'll go into the detail of this other part. Okay. So once I understood this flow chart, we will see the binary coded NSGA2. So what is important here? So we'll again just try to solve this problem so that it will be easier to understand. At least we'll do some sort of hand calculation, because Professor Mahapatra said that he is interested on some sort of hand calculation so that you can understand. So representing a solution, so minimize F1x, minimize F2x. Now, could you tell me whether it is a single objective or whether the objectives are conflicting in nature with respect to x1? Are they conflicting with respect to x1? Okay.
Yes, sir.
So, yes, of course, because if you see that if you try to minimize x1, this will increase. So this is a conflict. So I have to check it first. I have to check it first before applying multi-objective optimization. Now, what is important here? First, I have to, because I'm interested in binary coded NSGA2. So I have a decision variables x1. I have a decision variable x2. The x1, this is our this is a solution I have taken. How many bits? 1, 2, 3, 4, 5. Here also I have taken 1, 2, 3, 4, 5. So in 10 bits, make one solution. Out of that, 5 bits is for x1 and another 5 bits is for x2, right? So we call it chromosome or string. This is a genotypic representation of a solution. So x1, x2 is no more. x1 is going into the bits, x2 is going into the bits. You can increase these bits, there is no restriction, but you will sometimes increase the computational time. That's it. Now,
so that means sir, sorry to interrupt you, but that means this is a random selection.
Yeah,
or we have any method?
This is a random number. Use a random number. Just make an algorithm to generate a random number, and you choose the bit. But you restrict that how many bits you require to define one x, to define one decision variable. But whether 0 or 1, that will depend upon based on just an algorithm written for generating random number 0 to 1, right? So that is program is there, it is available. It's not a very big deal, but it's just just with the help of the algorithm generating random number. That's it. If it is 0.5 less than 1, we choose 0. If it is greater than 0.5, we choose 1. You got it? That's how we do that. Yes. So this is called a genotypic representation of a solution. But see, somehow some constraint is applied to your, some upper and lower boundaries applied to your process variable. Now, if you decode it, you'll have a more, greater value than this. Now, if you decode it, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, a lot of big value will give you. So for that, to make the solution lying within this range and this range, what is important here? I have to do a binary encoding. And that is what, this is typically a linear relationship and what is called binary encoding. And you see that the real value of, say, x1 variable, that is nothing but, the lower limit. What is the lower limit? So for x1, it is 0.1. We have to know what is the upper limit and lower limit. We know what this is. I hope this is, what is the value? Or x1, 1 minus 0.1. 1 minus 0.1, 2 to the power ALSI. This ALSI is the string length. So what is the string length for this x1 solution? 1, 2, 3, 4, 5. So we can either 2 to the power 5 minus 1 into XID, that decoded value. Decoded value means the decimal data, the binary data converted into decimal data by the formula like 2 to the power 0 into the value, 2 to the power 1 into that value, 2 to the power 2 into that value, and that we can find out this. And then finally, it will give a value which is definitely guaranteed. Guaranteed the value will be only between this. So this is why the binary encoding is very much important, just to map the arbitrary value, because the solution doesn't know. The solution, the initial population or initial solution you have chosen, it doesn't know whether it is lying between the upper and lower boundary is not. So it is you who has to forcefully convert into, either linear mapping rules, you have to convert into the within the boundary of this upper and lower boundary of this decision variable. So you have to do it for x1, you have to also do it for x2 using the same formula. Now, then this is another part, is the assigning fitness. Now, again, this you have to be very much clear that GA are suitable for only solving maximization problem. Because if you see the selection process, it's only based on the maximum value, maximum value of the fitness. So it is very much useful for maximization problem. So the question comes, can we not solve minimization problem? Of course, we can do, but you have to convert it. How? So for example, fx is fx. For maximization problems, there is no issue. But for fx, suppose you want to go for minimization problem, so what you have to do, the functions you have to convert into 1 by fx. Now, you are actually, if you increase fx, you are actually decreasing fx. If you are increasing fx, so we are actually decreasing capital fx. So that way, actually, you are actually solving, for minimization problem. For minimization problem, if fx, if you want to minimize, so this value will be maximum, because ultimately you are interested on maximization problem, right? So this minimization, you are interested on minimization of that. If you minimize it, automatically it will maximize. So that way you have to convert it. When fx not is equal to 0, but when fx is equal to 0, because fx it is 0, then it becomes infinite or indefinite. So to take care of this, you have to just add one value, so that this infinite loop, the program will never reach to the infinite loop, right? When fx is equal to 0, that much modifications you have to do. Now, this is very important of this NSGA2, which is called first non-dominated sorting. So we'll explain what is first non-dominated sorting. Now, if you see that one, so we have an objective function. Again, same problems we have chosen. This is minimize x1, minimize fx, f2x, x, f1x, and this is definitely I would say conflicting objectives. So what is important? So if you recall, when I was discussing about the flowchart, the working algorithm of NSGA2, you possibly recall that, if you recall, I would say, I told that all the solutions, whatever the initial solution I have chosen, I have to rank them. 100 solution, it is not like the solution is so good that they are all lying in rank 1. No. There may be some solution maybe lying in rank 1, maybe followed by rank 2, rank 3, rank 4. So I have to rank it. So ranking is done by this algorithm, first non-dominated sorting algorithm. How it is done? So we are interested to, for that we have to find out in the algorithm, we have to find out these two quantities. The first quantity Ni is known as domination count. Domination count. What is domination count? That means out of say I have chosen 6 solutions. Suppose the initial solution size is 6. Now out of 6, suppose there are 4 solutions which dominate solution I. Or rather, this could happen, like so there are 6 solutions. You chosen first solution, and you compare it other solution and check how many solutions actually dominate solution I. That means the first solution, suppose, and how many solutions the I solution dominate. I mean, so this is the 2 quantities. How many solutions get dominated by solution I, and how many solutions I dominates. Right. So Ni is actually representing how many solutions dominate solution I, and that is called domination count. And this is the number of solutions that solution I dominates. So you have to do it for each and every solution. How to do that? Now, if you have an objective function 1, so as it is a minimization problem, so I have to check. Say I have chosen solution I and solution J. We have a 6 solution, 1, 2, 3, 4, 5, 6 solution, right? So now I'm comparing this solution 1 to solution 2. So it is suppose I, this is J. I have to check whether objective 1 I'll just put the value of I there, or put the solution there. I mean the real value I have got, I have the input output relationship, objective 1 I know. So I will choose the value of x1 here. In F1, I'll choose the value of, because this is a function of x1. So for the first solution, I know the real value. I'll put here, I'll get F1. Again, for second solution, again, I'll put that value into F1. I'll get another objective. So I have to check whether this is less than this. And not only one solution, because this is a 2 objective function. So I have to also satisfy this one. Objective 2 for solution I less than equals to objective solution J. This is, or maybe less than equals to or less than. This is important. Otherwise, your program may sometimes, go into the infinite loop, right? So that is very important. In my PhD time, and I also stuck to that problem, and then concluded, no, I have to use this, less than equals to. Otherwise, sometimes the situation might sometimes come when they are equal, the program may go for infinite loop. So what is important here? I have to satisfy 2 objectives. How could I say one solution is better than other? If and only if the solution I has objective 1 less than objective 1. I mean, solution I has objective function 1 and objective function 2, both is less than for solution J. If it is happening, then I can say that the solution I is dominating solution J. But if it is reverse, then I would say the solution J is dominating solution I. I hope I can do that. If I make a program, I can easily find out, how many solutions are actually being dominated and how many solutions are being dominated and are dominating. That means for each solution, I must have a Ni value and Si value. Ni value means how many solutions. I'm just interested in how many solutions. 2, 3, 4, how many solutions are dominating, and this is how many solutions are just dominated, right? And to do that, what is important, if you see the computational in complexity may be mns square, where m is the number of objective function and n is the number of initial population. Say I have a 2 objective in this case, and say I have started with 8 population. So how many comparison required? 2 into 8 square. That means 128. 128 comparisons are required, and after that we'll get Ni and Sy for each and every solution. Now at this juncture I can say, suppose the solutions which have Ni is equal to 0. Suppose out of 8 solutions you found that 3 solutions have Ni at first point, when generation 1 is going on, you found that Ni is 0 for 3 solutions. What does it mean? Out of 8 solution, Ni is equal to 0 for 3 solutions. What does it mean? Can anyone tell me?
Participants, you can unmute and answer.
Okay, fine. So, okay, if you would have answered this question, now I would have very happy. At least I'm going into the right track. I mean, I'm able to convince you. But anyway, unfortunately, so if
Sir,
you
it may
find that
be
solutions,
sir, it may be a local optimum solution.
no, I'm not asking local and global. I'm asking that if some solutions are Ni value 0, what does it indicate? I mean, that indicates that there is no solutions. There is no solutions. I mean, there is no solution which dominate that solution, right? Say out of 8 solution, third solution has Ni value 0. There is no solution which dominates solution, say third solution. There are, say, solution number 5. There is no solution which dominates solution number 5. That means these are the solution out of 8. They are the best, and they deserve the first position. They should be in the rank 1. And then again, you do it for next one, rank 2 and rank 3. So that is how these things are, done. Now, to do that, say I have just given one data. If you see the solution 1, I have chosen 6 solution. These are the parent solution, and these are suppose the for the time you consider offspring, the children solution. So I have started with for 6 solution actually, but after one generation I will combine, and then I have another 6 children. So I have a 12 solution, suppose. And 12 solutions are this: x1, x2, x1, x2, x1, x2, and x1, x2. And we have also found out f1, f2, f1, f2. Everything I have found it out. So this table is very important. You have to store it in an array when you write your programming. You have to store it in a double 2-dimensional array. Now, what you have to do is that this is what I did. This is what I did. See, if you see out of this 12 solution number 4. So what this 12 solution? These are the 12 solution. The solution number 4 is this. It has a f1, f2 this much. The comparison is done, and then you can see that it is lying in front 4. I mean, okay, who is in front 1? Okay, this is front 1. This is front 1. So you can see in front 1, A, E, and 5. These 3 solutions are lying. These 3 solutions are lying. So they are the best. These 3 solutions are the best among 12. So 9 are discarded. So you do not deserve to be in rank 1 because you are inferior than us. A, E, and 5 says you are inferior than us, so you do not deserve to be here. So we all 3 are deserving to be in rank 1. You go, right? But again, what interesting point is that A, E, and 5, you cannot compare these 3. See, A, E, E5, this A is better with respect to F1. Maybe with respect to F2, it is not good. But F2, see, F2, you have F1 is bigger, but F2 is less. So that means you don't have a direct comparison. I mean, in both ways, 2 objectives are not satisfied among these 3. When absolutely satisfied, the 2 objectives, the relationship which I have shown less than, when this is satisfied, then I can say that they are definitely good. But here I cannot say good. So that is the importance of this non-domination principle, right? You can see in the rank 1 solution, I cannot say which one is better than others. But I can guarantee you that these are the solutions which are the best among the other 12. Among the 12, these are the best. So these are superior than this solution, and this solution. Then do it for rank 2. Then do it for rank 2. So this is a front 2. So all the solutions deserve to be, I mean, it's actually just inferior than front 1, right? But again, you cannot say which one is better. And these solutions are better than solution 2, C4, right? Again, you have a front 3 and front 4. So this is how things have been done. And you can also check, like, if you take this value, suppose this value. So what is the F1 value, something like that, and F1 value, something like that. If you take any solution, it will never give you that minimum F1 and minimum F2 compared to this, right? Now, this is again, I will explain with the help of this, very nicely made, this hand calculation, right? Now, if you compare, as I said, for each and every solutions, you have to calculate S1, N1. So for each solution, you have S and N. N is what I said is a domination count. That means here you can see is domination count is 1. That means there is only one solution that is better than solution number 1. And what is that solution? Is the solution A. Is the solution A. So solution A is better than solution 1. So it has a domination count only 1. And what is S1 here? There are 3 solutions, 2, 4, C, which are inferior than solution 1. So that's how we have to do it for S1, S2, S3, S4, S5, S6, then SA, SB, SC, SD, SC, SF. So I have used 12 solutions. So I have to have a S and M value of these 12 solutions. Now, what is important here? The algorithm now trace out of this N value, that is domination count, which one has a 0 or nil domination count. Let's check. Okay, NA. After the comparison, I could see that NA has a nil. It has no domination count. I mean, no solution is better than solution A. Okay, then go for where is nil? E. No solution is better than E, right? And then anybody else? Yeah, N5, also nil, is also nil. So I can just your program will trace which N value is 0. Now it traces that E has 0, N, A has 0, N, and 5 has 0, N. So these 3 solutions will come in the front one. So you can see here. So A, E, 5, they are coming in the front one solution. So as out of 12 solution, they have been taken out. So rest of the solution I have to discard it. I have to delete them. How to delete? Now you can see that NA I will go in the SA list. SA list. So SA list I will check. Oh, it's very big. I will go in this any. So I'll go with 4. Where is the 4? 4 is here. The 4 I will go into the 4 N value, domination count of 4. From here, what I should delete? From here, what I should delete? I should delete NE. I should delete NE because this is no more in this domination count because I have already chosen. So by that, you continue to do that. And sometime it will come, just continue to do that. Sometime it will come that slowly, जो N4 यहाँ से कितना count हुआ? 1, 2, 3, 4, 5, 6, 7. 7 count. I think this will go to last front, and maybe you will start with this NC. See, you have discarded A, and so after discarding this, sometime NC will become 0. Maybe front 1, front 2 के बाद NC becomes 0. So it is becomes 0 means now it deserves to be in that rank, right? So like that, you have to carry out this first non-dominated sorting. I think I can explain a little bit so that okay, fine. So this is from S4. I've deleted E. Now let's take this one. Where is Neil? Yeah, here. N5. So I'll go 6 and B. Where is 6? 6 is here. So 6. So from 6, I shall delete 5. Again, I shall go to B. Where is B? B is here. So I shall delete 5. So now see, after deleting NB, that has no domination count. Domination count is become 0. That means there is no other solution which can dominate. So after solution 5, that is the best one. So I can put it in the rank 2 solution. So this way, your algorithm that has to be written in such a way that this will continue to do that, and finally it will find out a 0 domination count, and as per that, it will rank them. Now, once I understood this, so finally, after carrying out this algorithm or applying this algorithm, I have found that in the front one, that means rank 1, we have 3 solutions. Rank 2, we have 4 solutions. Rank 4, we have 4 solutions. And in the rank 3, we have 4 solutions. And then rank 4, we have 4 solutions. Sorry, only 1 solution. Now, what I can say that rank one solution, that means solution number 5, A and E, they are absolutely better than any solution lying on M2, F2, F3, F4. Or I can say that any solutions lying on FT, F2, that is 1, 3, BD, they are better than any solutions lying on F3, F4, but they are inferior than any solution of 5A and E. But again, another point, I cannot say which solution is better than the other lying in F2 or lying in F1. So they are equally important. So that is the beauty of multi-objective optimization. Like, in real optimization problem, real world, we are interested on the multiple solutions. And those solutions should be the best out of the million solutions are available in the feasibility domain. But that should be the best one. And you cannot say which one is better than others. You cannot say. Like, I have explained one example, like cost of the car and comfort of the car. You see, you have multiple solutions. You have got that one line. And this is consist of different solutions like this. And that is the best out of the million solutions, something like that. So this is what is called first non-dominated sorting. Now, the next part is important is the crowding distance. So what is crowding distance or why it is important? It is, so when the ranking is done, then for each solutions lying in each front, I have to assign a crowding distance. Why crowding distance is important? As I discussed, that there might be possibility that in some rank, the solutions are lying in a very close to each other. I do not want those close data, because they are actually representing a single type of solution. I want to diversify, and to make a diversification, this crowding distance will be required. So that is the purpose. But first, let me check or let me know how crowding distance for each and every solutions lying in a particular front can be calculated. So this can be done by this formula. All right. So what is that formula? I'll explain in details. This is IM. What is IM? This is crowding distance for objective function 1 for solution number R is its crowding distance for objective 1 plus the fitness function of the next minus the previous one divided by the maximum fitness function and minimum fitness function. Now, I thought it's not making any sense if I go like this. Let's go into some systematic analysis of this equation. What does it mean? So we'll do a hand calculation. Now, just I have chosen only one front. If you recall, just we have got a different front solution. If you recall, in front 2, there are 4 solutions lying: 3, D, 1, and B. 3, D, 1, B. These are the solutions lying. So each solution has a specific fitness function. I have given here also. Solution 1, 3, B. Okay, this should be small b. B, D, and the fitness function I know, F1, F2. I know everything, right? And they're lying in front 2. Now, what is important here? First, I have to sort them, because it's a minimization problem. I have to sort them in big to small to big fashion, right? That means, ascending order, small to big, ascending order, with respect to fitness for first objective, for first fitness function. So if I do that, just check this value. I mean, which one is the smallest one? I think among these 0.27D. Okay. Okay. 3 is where? 3.22. 3 is the smallest one. Then D, then 1.31, and then B 0.71. So I have just in the program, in your algorithm, you have to write a for loop to do that. This you have to do that. You need a separate for loop for that, doing this. So we have a 3D, 1B. These are the solutions, right? I mean, ascending order according to fitness number 1. I have did that. What I will do right now, I will assign infinite value 3 to B. That means why I'm trying to put as infinite value. I'm putting infinite value because I want to make sure that any solution lying at the extreme position, they should not be discarded. They should be there in the next generation. And for that, I assigned a very big value. And the big value is, I said infinite, but I have to put in a 99999 some value. Infinite you cannot put, but 9999 and a very big value you put there, so that there is guarantee that these two solutions, 3 and B, will be every time chosen in the next generation. Now, then for the rest, we have a rest means D and 1. For this solution, I have to find out the crowding distance. So the crowding distance I have assigned infinite, so that this will be selected by guarantee, right? But D and 1, which one I should choose? Which one I should choose? Why which one I should choose? It means, I mean, see, as I said that I have combined 12 solutions, right? 6 solution parent, 6 solution offspring. And I have combined them, but out of 12, again, I have to take 6 solution only. And while you're doing that, just go back a little bit, go back. Yeah. While you're doing that, so I have 12 solutions and I have ranked. Now you have 3 solutions in the first one. I will definitely choose them for the next generation. And then I shall move into rank 2. Now in rank 2, we have a 4 solution. If you add 3 plus 4, that becomes 7. How many I require? Only 6. I can take only 6. I cannot take 7. So I have to now take a decision. Out of these 4, which 3 I should take? So that is the importance of crowding comparison operator. So crowding distance will tell you which one, because they are lying in the same rank. So you cannot say which one is good, which one is bad. To do that, you have to have a crowding distance. And crowding distance is nothing but only to maintain diversity in the solution space. Now, how this diversity is maintained? If you see, this crowding distance is nothing but giving an idea of average perimeter of the cuboid which you draw adjacent to the covering the neighboring points of the solution for which you want to find out the crowding distance. So for example, if I take solution 1 and I want to find out the crowding distance, so what I will do, what are the neighboring points? Neighboring solution is D and neighboring solution is B. So what I will do, I will draw a cuboid and the vertices will be the adjacent solution, right? Corresponding neighboring solutions. Now, what is the average perimeter? This, if I know this F1 for B minus F1 for D, this is one, and then I will do F2 for D minus F2 for B. That means it will giving this length and this length. So crowding distance will just simply will be doing this one. I have written so big equation, but it actually is doing this one. So it will actually calculate the average perimeter of the cuboid which you draw considering 2 neighboring points for the points which you want to find out the crowding distance. Now for 1, you can see the crowding distance is very big. And for D, what are the solutions? Solution is 3 and solution is 1. So you can see the perimeter will be less. Perimeter will be less, right? So this is bigger than this. Now what does it indicate? It indicates that out of 3 and B will be definitely chosen, selected. But out of D and 1, which one I should choose? Whether D or 1? What will be the answer? Could anyone tell me? Which one I should choose, D or 1 from this cuboid perimeter, from the average cuboid perimeter? Of course 1, because the 1 has a max. Yeah, tell me.
So D has more perimeter, so we have to select 1.
Yes. So the perimeter is the average perimeter is big 1. Is bigger for 1 compared to D. That means I could say that 1 is one is more compared to 3 and D, one is more diversified, because if I have chosen D, so D is more close to 3. D is more close to 3. So they're same. But if I choose which I have chosen 1, that is more diversified. So D I should not choose. I should delete D. So I should choose, this 3 out of 4, I should choose only 3, 1, and B. That's what, crowding distance, crowding comparison operator is doing. So let's see that this is what I do. I'll do that. So yeah.
So
Yeah,
crowding
please.
distance and crowding distance is also similar to we have to calculate Manhattan distance.
Which distance?
Manhattan distance.
Manhattan
and Euclidean.
No, this is not
Manhattan. MAN.
Okay, so I'm not aware of this.
Manhattan distance.
No, I'm not aware of this. Sorry, I'm not aware of this. The Euclidean distance I know, but the formula is different to calculate Euclidean distance. Generally, we use Euclidean distance in radial basis function network for K-means clustering algorithm. We generally use a Euclidean distance. Yeah. Yes. So for 2 solutions, I have already set infinite, but other 2 solutions I have to find out. So this is for function 1 and function 1, solution D and solution 1. I have to find out the crowding distance. So this will be with respect to objective function 1. So I shall put what is F1 for solution 1, what is F1 for solution. How 1 and 3 I have got? Because these are the neighboring solution adjacent to solution number D. So I'm finding out crowding distance for solution number D for objective function 1. For that, I need 2 neighboring solution fitness. And I know also what is the maximum minimum value. If I put that, I will get crowding distance 0.1. Similarly, I have to do it for solution number 1, because there are 2 solutions for which I have to find out crowding distance for function 1 and function 2, fitness 1 and fitness 2. Similarly, we have a B and D. These are the neighboring, and I have got 0.5. So one step is done. The next step, then again, what you have to do, you have to again sort the solutions. Which solution? B1, B3. These are the solutions. See, if you go back here, with respect to F1, this is the ascending order. This is the ascending order from small to big. But with respect to F2, this will be the ascending order. So I have to, in the program, it has to be there. You have to find the ascending order distance. And then again, as these are at the extreme, so you have to assign infinite here, infinite here. Now again, I have to find out the crowding distance for this. So one crowding distance I have found out for fitness 1 and function 1, and another crowding distance I have to find out for function 2. But again, what I have to do, whatever the crowding distance I have already obtained, I have to carry forward this. I have to update it. So this is for F1, and I have to update it for F2. So initially, whatever the value was there, it will be there. But now, again, F2, so now it's become F2. Again, the solutions are 3 and 1 for finding out D, crowding distance for D. And F2 max, F2 min, So finally, it is updated to 0.2. And I21, finally, it is updated to 0.63. So what is the final overall crowding distance now? So for solution 1, it is 0.63. For solution 3, it is infinite. For solution B, it is infinite. And solution D, it's for 0.12. Now, I have to sorting. I have to do a sorting, crowding distance for descending order. So descending order, if you set it, it's become 3 because infinite. B is also infinite. 1. What is the 1 value? 1 is 0.63, D is 0.12. So 1 is bigger than D. So I shall choose only these 3. I shall discard this. I shall not carry over this one. So in the next population, you can see I have chosen 3 solutions from front 1 and only 3 solutions from out of 4 in the front 2. And this is done with the help of the crowding comparison operator, which I have explained very elaborately. Now, again, as I said, this is after recombination, this part is required. But what is important here is also crowding tournament selection. As I said, in single objective GA, you might have observed some sort of reproduction technique or selection technique, such as tournament selection, proportionate selection. We sometimes call it as relative selection. Sometimes we use ranking selection. Similarly, here we are using crowding tournament selection, right? That means we have a 100 solution, parent solution, 100 parent solution, 100 parent solution. Now I have to create 100 children. 100 parent can produce 100 children. So again, we will get 100 children. How will I get this 100 children? In single objective GA, as I said, we use say proportionate selection. So maybe after reproduction, the mating pool might reproduce more number of good solution. So bad solution will go, more number of good solution. Maybe if you move higher generation number, you will see the mating pool will consist of maybe 2-3 solutions. And after that, maybe it will converge into 100 solution. In the 100 solution, you have only one solution because the best is copied. But here, how it is done, how it is copied, say I'll compare this and this. I'll compare this and this. Maybe I can give 2 chances for every solution just to compete with each other. Now, when they are competing, so if they are in the other rank, say 2 solutions I have chosen, this solution and this solution I have chosen. Okay, for what? For reproduction, right? Now I'll see that first I will see that whether this has a better rank than this or not. If it has a better rank, this one has a better rank than this, which one I should choose? Tell me. Yeah, can anyone tell me which one should I choose? Either this one or that one? So I'm competing between this and this. I'm picking these 2 parent, and from there I want to choose which one it should be in the mating pool. Of course, rank 1 solution, this solution, because it has a better rank than this. No issue. This will definitely go there. And the second option, which I discussed so far, is that suppose this is one solution and this is another solution, and they are in the same rank. They are in the same rank. So you cannot absolutely say which one is better. So then what I have to do, I have to check the crowding distance of this and crowding distance of this. So which one I will choose? I will choose the solution which will have a higher crowding distance. So that is the crowding tournament selection. So if the solution, if you chose 2 parents and if they are in the same different rank, so the better rank solution will go to the mating pool. Similarly, if the solution chosen lying in the same front, then I have to choose the higher crowding distance to maintain a diversity in the solution. So this is how the crowding tournament is done. And then after that, we have to apply a crossover and a mutation, as it is 2-side, 3-side crossover with a crossover probability, then mutation with mutation probability. And by that, we can have a what is called offspring, 100 offspring. Then in NSGA2, what I have to do? So this is a P and this is Q. So this is 100 and this is 100. I have to combine. So I will combine this 100 plus this 100, and then again I will do what? Sorting, crowding distance, and out of this 200, I have to choose only 100 solution, and then it will go to the next generation. That's how the NSGA2 will work. Now finally, interestingly, you see a Pareto front is obtained. So very nicely, this is our solution we have obtained using the code which I have written in only C, not C++ also. With the help of this after generation 250, and this is the population I have used 100 and mutation probability 0.9. Finally, I have got a Pareto front. So this is a Pareto front, multiple solution. I hope there are 100 solutions there. This is a Pareto front, which is the best out of a million of solutions. And not only that, we cannot say which one is better than others, right? Right. So this is how it works. Then we have to again go to the real coded. So real coded, there are some problems. I don't know whether if you are working on real coded, possibly you might have come to know what are the different difficulties in binary coded in SGA. First one is the arbitrary precision in optimum solution. That is difficult to obtain. The reason is, if you want to increase the precision in the optimal solution, you have to increase the bit size. And if you increase the bit size, you are increasing computational time. So that's, you have to make a trade-off. That is one. Second one is fixed coding scheme. Just that one coding scheme I have used to map the decision variables from binary to the real value. And there you might have observed that we have used a maximum and minimum value of the decision variables. Now, it indicates if you know the boundary values of a decision variable, that means you are very much sure about the problems. You know that this is the range of optimal solution. But in the real world, it will never happen. I mean, it's not obviously possible every time that you know what is the range of this input decision. You do not know anything. And for them, it is quite difficult to, then this fixed coding scheme might create a problem. If you do not aware of the boundaries of the decision variables, then you cannot apply this fixed coding scheme. Then there is another problem which is called Hamming-Clips problems. So if you see this genotype and this string, to change into its next neighboring value, a real value, you have to have a change over these 4 bits. You have to change this, you have to change this, you have to change this, then possibly you can go to the higher value. Similarly to that. That means you need to have a more number of bits that has to be changed, which is very unlikely, because the change of bit is happening because of crossover and mutation. And mutation is generally happening with 1 bit, or crossover maybe happen in 2 sides, or maybe sometimes 1 side. So changing these 4 bits just to move into the next real values, it is hardly happening. And when this problem will be associated, then it is called a Hamming-Clip problems. Now, the working principle is simple in NSGA2. I mean, you can also use non-dominated sorting. Fitness function, you can find it out because you have a direct real value. You can already find out the fitness function. You can do non-dominated sorting. There is no issue. You can also assign crowding distance. There is no issue. Up to that, the program will remain same. But from here, it is going to be changed. Even the crowded comparison operator, crowded tournament selection, that can also be applied in real coded NSGA2. But what you cannot do is the crossover and mutation, because in binary crossover, exchange of bits is possible between 2 parents. But in real code, how will you do this exchange, right? How will you do exchange? And for that, again, there are several algorithms available, and one of them is simulated binary crossover, which is developed by Professor Dev and his team. And just I can tell you this one thing is there, that this is how after finding the alpha 1, this is how finally you can find out children 1 and children 2. And then in the polynomial mutation, sometimes we use this perturbance factor, and using this formula. This is a random number you have to generate, and based on this formula is to be used. And finally, the muted value will be original value plus the perturbance you have calculated and the maximum. So this is how muted has to be done in real coded NSGA2. Now, the next part, which is also very important, is the constraint handling. So, Professor Mahapatra, I have to be till 1:30, right?
Yes, sir. It is actually it is. We can conclude it between 1 p.m. to 1:30. Okay,
fine. Okay.
Yes.
So you can see that the constraints. If you look at the constraints, the problems which I have solved so far is only the constraint given on the decision variables. But this kind of constraint has not been imposed, right? Same problem we have chosen, but the decision variables has not been taken. The constraint has not been taken. So what is the extra constraint? These 2 constraints are there. One is that x2 plus 9x1 has to be greater than 6. So this is very common in real world optimization problem. And the second constraint is that minus x2 plus 9x1 has to be greater than 1. So now I have to find out the solutions, Pareto solutions, which will also satisfy this constraint. So this is I didn't discuss so far. I discussed so far unconstrained kind of problems, right? Now let's see how it could be solved. Now we have 6 solutions you can see. If you impose, this is the same fronts which I have got for 6 solutions. Yes, front 1, front 2, front 1, front 2, front 3, and front 4. 4 fronts we have assigned the 6 solutions, right? And this was unconstrained. But when you impose the constraint, you see the solution space is this much. This is the solution space. If you apply the 2 constraint, this becomes your solution space only, right? So that means these solutions 3, 1, and 2, and 2, they're all lying outside of this feasible solution domain. So which is not feasible. I mean, energy to the solution, even the Pareto front, you can check. So all the solution up to this, all the solutions which you have got, they all will have to be discarded because they are not lying in the solution domain or the feasible solution domain, right? So something has to be included in the NSJ2. And there are several methods again available, sometimes ignoring feasible solutions, methods based on penalty functions, constraint, tournament method, and precise use method, but we shall only focus on these penalty functions methods. Now, what is penalty function method? It's very simple. Let me just explain what is that first. Okay, just go by one so that I can conclude. First of all, what I have to do, I have to convert this constraint. I have to normalize this constraint. That means everything should be, in the right side, there should be 0 only. I hope you can do that, this one. Everything I have kept in the left side, and right side we have made 0. So this form is called normalized form. So the constraint has to be first converted into normalized form. Now, what is the next step? The next step is I have to find out what is called a constraint violation. Constraint violation. Who is violating? I should penalize. Who is violating the solution? Who will be going to? Who is violating this constraint? I should penalize. How should I penalize? To penalize, I have to find out this constraint violation. Constraint violation. So this is the equation to find out the constraint violation. What is that? What does it say? Say Gj. I have just taken the mod value. What is Gj? Did I use the Gj equation? Yeah. No, it's not. Okay. Gjxi. What does it mean? It means that I have 2 constants. So J will be 1 and 2. So G1 and G2. For G1, say this is the ith solution. So I shall put the ith solution in G1, and I will check whether the condition is satisfied or not. I mean the constraint which after normalizing, whether it is satisfied or not, whether it is greater than 0 or not, greater than equal to 0 or not. If it is less than 0, that means it is not satisfying, or constant is not being satisfied. Then I shall just put the mod value. Whatever the G value I have got, I mean constant value I have got, I shall simply put it, but the mod value I shall take. And if I found it is satisfied, then I am not going to penalize, so I am not going to use, I just put 0 value. Now, why this is required, just you will understand after this step. Now, what I have to do, I have to add all the constraint violations. So I have a constant value violation for G1, I have a constant violation for G2. For G1, we have to check whether it is less than 0 or greater than 0. If it is less than 0, I have to take the mod value. If it is greater than 0, it will be simply 0. Then I have to do it for Z2. Again, I have to check this. Now, so I have to sum it up. So this is the amount. This is the amount that has to be added to each and every fitness function, existing fitness function. Now, why I'm doing this? Because I have to penalize it. I have to give a more value because I'm doing minimization problem. I will add it. I'll just add it. Add some big value there, like we did in crowding distance, infinite value. So I'll put big value there. I'll penalize by putting big value, adding big value there. If I put in big value, so it is guaranteed that it will not be selected. It will not be selected because of the minimization problem. So now for feasible solution, the solution which are feasible, even after doing this value will be 0 because I need not to change it. I need not to penalize it. So I am not adding anything to the already obtained fitness value. Whatever the fitness value is there, it will simply the comparison will be done. The ranking will be done based on the existing fitness. I am not going to add any value. If the solution satisfies the two constant equation, right? That is the meaning. Then finally, what I have to do, that's that things I have told. If you got some this value, if you got some this value, if it is 0, if you say it is 0, that means whatever the solution, whatever the fitness value you have, same fitness value you can use. But if it does not satisfy, even any one of them, if it does not satisfy, then these values will come with the multiplication of some factor, just to penalize the fitness, so that you should not come to the solution, right? So I think you can also understand by this simple calculation. Now, how to calculate the overall constant violation for first solution? If you see the G1 x1, so that means first constant for solution 1, this is the value. Now, this is it greater than 0, greater than equal to 0? No, it is not 0, less than 0. So that means it is violative. That means I have to penalize solution one. Solution 1 should not go to the next generation. I should penalize by giving more value into its existing fitness. So now W1 x1, as I putting the mod value, I'll just assign 0.39. Now let's go for second constant for solution 1. It's become 0.9. That means it is what? It is positive, greater than equal to 0. That means this will be 0. This will be 0. Now, so W1 x1 is omega 1 x1 is 0.39 and omega 2 x2 is 0. Why 0? Because it is not violating the second constant. So now I have to find out the total violation amount. So that has to be sum it up. And as there is two constant, I have to say x equal to 1 to 2. So we have a omega 1, we have a omega 2. Omega 1 is 0.39 and omega 2 is 0 because this is not violating. So finally, I have got a value of 0.39. Then what I have to do? I have to find out the new fitness function. How will I do that? Whatever the existing value is there, and then I have to add this violation amount. Now, for solution 1, already the fitness was 0.31. Now I have got this value, this omega value, right? This omega value, this penalty parameter. And again for F2, I have already that solution, and I have also got one what is called depenalized value. Now you can see I have used a 2 multiplication factor and 20 multiplication factor. This completely depends on you, because if you see the value, fitness value 0.31 and 610, so they have a different scale. At least I would say 20 times, right? This fitness and this fitness are the 20 times variation. Just to maintain this order, here I have multiplied 20 and here I have multiplied 2. Finally, I have got 1.09 and 13.90. So what is the next step? Next step is that we have a solution 6. We have a fitness 1, fitness 2. See, this value I have find it out. And see, for solution number 4, 5, and 6, there is no penalty because they are satisfied. But this gets penalized because these are not satisfied. So when I calculate the fitness function, the updated fitness function on which the ranking will work, the non-dominated sorting algorithm will work, will be changed now. Now you can see that F1 and F2, they are remain same. See, F1 for solution 4, 5, 6, whatever they were initially, 0.59, 0.66, 0.80, they remain same. Even F2 also, they remain same. But what is changed? These values are changed. Why I'm changing it? I'm going to penalize it. I cannot use this value. If I would have chosen this value, this F1, if I would use that one, then by chance it can be selected, and it can again go outside the feasible solution domain. So to ensure that my solution should be in the solution in the feasible solution domain. So that's why I have put bigger F1. So see, F1 is initially 0.31. Now it has become 1.09. It was 2.73. I don't know, it is 1.0. So I have to check it. Then this is 0.56. This become 1.38, right? Similarly, sorry, I have seen this one. I have to choose this 0.38, 1.06. Similarly, you see F2 6 point. It's become 13 point. 9.82. It becomes 16.60. 7.09. It has become 18.9. See, initially, whatever the solution in the rank 1, now the crowding sorting will be done based on this F1, F2, not this F1, F2. So when you do that, the ranking will be again changed, and you will see that now the solution 4 and 5, they are coming in the rank 1 solution, and solution 6 is coming in the rank 2 solution, and 4, 3, the other solution. So this can be shown here. See. So only 5, 6, 4, they are coming here, and other has been shifted. The rank has been different. Initially, the rank was maybe the 3, 1 was in the first solution. Now this become solution. Third rank. Now it's become fourth rank solution, right? So there has been outside it. Now only I have got 4, 5, 6 this solution, and which is in the domain only. But again, what I have to do, I have not shown here. Again, I have to also find out the Pareto font. I have to also find out the Pareto font, and the Pareto font may be like this, because the Pareto font which I have got is again outside it, which is not acceptable. So it has to be here. It has to be here, right? So this is how the constant can also be handled in NSGA2. Now there is another very in our time. I don't know now what is going on. In our time, that is the hot cake, Neuro NSGA2. The really hot cake. People working on that definitely will publish one paper, right? So Neuro NSGA2, the only difference is that the working principle is remain. Only difference is that the fitting function, the fitness is obtained by what is called the neural network, right? Neural network is used for the getting the fitness function, and other steps will remain same. So only thing is that you have to whatever the algorithm you have written for neural network, that has to be coupled with the NSGA2. Of course, it will be a very big program, and there you can easily find out what is your neuro NSGA2. But mind it, you have to train the neural network separately, because you have to obtain the the optimal architecture of the neural network. You must know how many hidden layers I have to use, how many nodes should be there in the hidden layers. Everything has to be known prior to that, and then that optimized value you can use it in the neuro NSGA2. Now, so far application is concerned, this is, I will not go into details of that, but what I can show is that just I'll show some results out of this. I will not go into details of this. I hope it is visible. So just I have applied it to wire electrodischarge machining. I think everybody knows it. The working principle is similar to EDM, but only difference is that the wire is acting as an electrode, but the material removal takes place with the form of discrete sparks. Now these are the typical parameters. You have a pulse on time, pulse off time, peak current setting, gap voltage, capacitors. A lot of parameters are there. And in the output side, you have a cutting speed, surface roughness, and curve width. Now what we did, we actually worked on metal matrix composites. So I will not go into this. I will not go into this strictly. I should go just. I will first go. Just made a modeling of this, right? This I will not go into this. Yeah, so I did the modeling first. So modeling, we've done this RSM, response surface modeling, then BPNN, back propagation neural network, then normalized real basis function network, with traditional k-means technique, enhanced k-means technique, gradient descent technique. So all these neural networks coding has been done and then applied to this process. And then, yeah. So in our case, the objective function was, the first one is the cutting speed, which I want to maximize. And objective 2 was a curve width, which I want to minimize. So I just converted into suitable form 1 by curve width. And then finally, you can see that after running this program, so this is the initial solution, which are very scattered in nature, 100 solution, cutting speed versus curve width. You can understand that they are not the Pareto solution or optimal solutions. But after just 13 generation, you see this kind of solution is been aligned particular direction. And you can see there are only 4 rank. Just after 13 generation, all the solutions are converged into only four rank solution. And finally, what you can see that I just applied all type of neural network here, NSGA2 BPN, NSGA2 normal k-means, NSGA2 enhanced k-means. So all these algorithm I have coupled for find out the fitness and just trying to find out which neurogenetic tools will give you the best results. But from here you can understand that NSGA2 with k-means that will give you the best solution. Usually for same cutting speed, the curve width is minimum. Same cutting speed, the curve width is minimum, and that is what is desirable. Same cutting speed, the curve width is minimum, which is more desirable. So that's all. This NSGA2 with enhanced k-means that was giving the best Pareto solution. So this is a Pareto solution, right? Now, just some of the parameters you should know, the range of parameters. So for bit length T on, T off, wear feed and voltage, I have used 10, 15, 5, 10. That means 10 plus 10, 20, 20, 35, 40 bits. One chromosome consists of 40 bits. So you can understand, some time is required. Definitely population size I have is 100, maximum generation 250, mutation type bitwise, mutation probability 0.1, crossover type 2 point, and crossover probability also 0.9. Then also just I want to check, I just check whether this method is indeed is good from the weighted sum method or not. So what I did, I hope Kamal might be knowing. Kamal, probably you can remember, because we made one single objective GA also for your paper, right? And there the same GA, same single objective GA that I have coupled with NSGA2. Now what I did, I just convert the 2 objectives into a single objectives first, and then I will introduce weighting factor. So weighting factor is 0 to 1. Now with the increment of 0.01, I solve the same problem. So this is a single objective GA. This is based on single objective GA. I convert the multi-objective into single objective, and then I run this single objective GA. With the increment, with changing weighting factor from 0 to 1, I just replace the weighted 1, say for 0.01, then again increase by 0.01, something like that, and I have got different solution. So you can understand that for 100 solution, I have run it for 100 times. 100 times I have to run this program, and then finally I've got the solution. And this is in one shot. This is in one shot. Not only that, interestingly, you can see the solution even is inferior than this. Why inferior? First one is they're gathered. See, these are all gathered. The solutions are not, diversified. They're all gathered, concentrated at some space, which is not desirable in real design domain, right? And this is only because of, NSGA2 use a crowding comparison operator, whose purpose is to make a diversified solution. Otherwise, it would have lead to this. Second one, for the same cutting speed, you see the curve width is higher, which is not desirable. For same cutting speed, I wanted lower curve width. So you can see for any solution which is lying in the NSGA2, is even better than this weighted sum method. So that way, Neuro NSGA2 is so excellent and can solve your problem. I mean, it can provide a big data optimal solution, Pareto solution to the process engineer, so that they can choose out of these 100 solution. So I hope, I must stop right now. I have other things to say, but again, I must stop right now. So Professor Mahapatra, this is from my end.
Sir, they have raised few queries.
Yeah,
so if
of
you
course.
can address them.
Yeah, of
One
course.
is, which programming language is good for GA?
Which programming language good for GA? No, in our time we use C, even not C++. But again, I would say that C will work. I mean, that is absolutely fine. But now people are moving to Python, something like that. And more interestingly, now if you see MATLAB, so MATLAB has a definite. They have a separate tools for genetic algorithm for single objective GA, for multi-objective GA, NSGA2, even some other kind of things. So just writing one line or two lines, even you need not to write a lot of things, only one line or two line, you can get the same solution. But the only thing is that the dangerous part is that you have to know the hidden algorithm which I've discussed today. Right. So the hidden algorithm should be known, and then you go for MATLAB programming also. That way, you can save a lot of time. You need not to go for make a code for this, because the codes are now available. In our time, maybe that was not popular. The open source are not available, but now it is available. Unnecessary, you will invest time to write code for NSGA2 or GA. So these are the available. Even in MATLAB, you can definitely get it. Okay.
Yes, sir. Any other queries? Participants, if you have any more query, you can go ahead and ask.
So is it made really valuable to you or not? At least say yes or no. I mean,
Yes, sir,
just
they are writing yes, this is a valuable session for them, useful session for them.
Yeah, Professor Mahapato, you said that they want very hands-on. So I think that is indeed hands-on, and
Definitely,
yeah,
it was a really nice session and productive as well. They are writing, it's a valuable session. Few of them means they are specifically means they are proposed for this type of session only. So thank you very much means for providing us with this type of presentation and information.
Yeah, thank you. So
So shall we conclude now, participants,
yeah,
or if you have any query, then you can go ahead. Else, we'll conclude this session here.
okay. So I can leave right now, right?
Yes, sir. Again, sir, thank you very much for accepting the invitation within a very short span of time.
Right.
We look forward to listen to you in future as well.
Right.
This time, I will I will let you know prior to greater. I will provide you a
Yeah,
greater
it is
period.
better. Like it is always better to at least give 1 week, so that I
Yes, sir.
I mean, in the morning I just spend almost 10 to 12 hours, just make sure that everything should be communicated in a better way, in a very comprehensive way. That's I try, and I hope
Yes,
that's
sir.
how I will
It
handle
was
that.
a really nice session and informative one. Thank you, sir.
So yeah.
Thank you very much.
Thank you. Okay, sorry.
Participants, you may leave now. You can rejoin for the third session at 3 p.m. So see you at 3 p.m. Thank you.